In some situations, the forcing acting on our system may be aperiodic, or it might be periodic but made up of discrete force events. In this case, it may be advantageous to not use the Fourier series expansion covered in the previous subsection because there might be a more direct way to get our closed form solution. It may be more compact, and it's not going to involve an infinite series. We encountered some of these in system dynamics, and we'll encounter some more types of forcing where possibly there is already a closed form solution if we do a Laplace transform. Or from your ODE class, you may have already seen what the closed form solution looks like to these types of forces. However, we're not going to go into the Laplace domain in this course. We're going to stick entirely in the time domain, but the solutions we're going to see could be found using a Laplace transform and then doing an inverse Laplace transform to get our complete solutions. And note that for almost any forcing we have on the right-hand side, we can do a Fourier series expansion on it, and we can get an exact solution if we take an infinite number of terms. So the solutions we're going to be seeing are identical to those we would get if we did the Fourier series expansion. However, we don't need to use that infinite series in order to obtain the same answer. So we'll be covering 3 distinct types of forcing that we might see on the right-hand side, and then how we can put them together to form more complex types of forcing. These are not the only 3 types of forcing that we can get closed form solutions for, but for this course, they're the only 3 that we will be covering. So first, we're going to look at what if our force is an impulse or an impact. It will be the same idea. We have a very short duration force being applied to our system. So we see in all of these events, the left-hand side is going to look like that standard second-order system we've been working with, 1 degree of freedom, but the right-hand side is where it's going to differ. So on our right-hand side, if we have something that's an impulse or impact, we're going to have some amplitude f times this delta t, where delta t is the Dirac delta function. So it's this instantaneous force that's being applied to our system. And f, the amplitude, is the amplitude of this impulse. And recall then impulse is the change in momentum of a system. Now likely we've seen this solution before in our ODE class, and impulses appear on the Laplace transform table, so we could get from that our closed form solution. So that's where this answer is coming from. That's where this closed form solution comes from. So in the case of an impulse, we see that the response of the system is going to be this exponential times a sine function. So we will see oscillations due to the impulse, and they're going to exponentially decay as time goes forward. The second force that we're going to consider is a step force, or a step input. And we've spent a lot of time looking at step inputs into second-order systems in system dynamics from a Laplace transform and a transfer function approach. Here we stay in the time domain. So the right-hand side, we can model this as some amplitude times a Heaviside or a step function. So recall that this h of t is going to be 0 when the argument inside is negative, and it's going to be 1 when the argument inside is positive. So we have some set amplitude that turns on at a certain time. We're going to see its closed form response is going to be an exponential times a trig function in a kind of similar manner that we saw when we were looking at the impulse. So it's going to oscillate, and those oscillations are going to die out. However, we'll see what happens unlike the impulse. As t goes to infinity, this whole term is going to go to 0, and we'll be left with 1. So the step force, we're applying some force and we leave it on, and we are going to have some constant non-zero displacement in our system as time goes forward. And we saw this all the time in system dynamics, that we had some initial position, we applied our step force, and now at steady state, we had a different position in our system. And there'll be a phase involved, this phi value, and the phi is going to be dependent on the damping ratio in our system. And the final force that we're going to consider is a ramp force. So this is a linearly increasing force being applied to the system. So on the right-hand side, we have this amplitude f, but here f is going to be measured in force per second. So initially when time is 0, we're applying no force, and then we are going to linearly increase that force as time goes forward. So once again, when we begin at rest, we're going to see our closed form response in the system. So what's going to happen when time first begins is that this t is going to be basically 0. We're going to see that this is equal to 1, this sine term will be 0, and this cosine term will be 1. So initially, we're going to see x of t remain small, or initially it's going to be at 0 as this 2 zeta over omega n's are going to cancel. But then as time goes forward, we will start to see some oscillations that decay as that time goes forward. So these three are only 3 examples that we will look at in this course: the ramp, the step, and the impulse. But we can actually combine them to get more interesting profiles that are made up of one of these that repeats, or maybe several of them that are going to be added or summed together. When that's the case, we can make what we call an aggregate force profile. So we can put multiple of these steps, impulses, or ramps together. Now, if we want to use this approach to solve for the closed form behavior of our system, we just want to make sure that we exert our force equation in a pretty specific way that's going to use a piecewise function. And specifically, it's going to be a piecewise function where we're going to keep adding more forces onto the forces that already exist. So we need to write our force in this sort of manner. So we're going to initially have one force, we'll call it F1 of t, and then we'll see what happens when we move on to our second interval. So it's this force being applied over this first 0 to t1 interval. Then we move on to the t1 to t2 interval. So notice what's happening. F1 of t is always present, and it will keep going down as we add more and more of these intervals here. So the F1 of t is introduced, and then in the second interval, that is where we are going to introduce this F2 of t minus t1. So a second force enters in the second interval. Those two forces, F1 and F2, then get copied for the third row, where we add on an F3, and so on, copying everything from the row above, and then adding another force. And we'll see in the examples what making a profile like this is going to look like. But if we write our f of t in this manner, where we keep superimposing another force on in every interval, that's going to make finding the closed form response simpler. For every one of these forces, F1, 2, 3, 4, we're going to find the response using the slides, using the equations from before, due to just that force. And then what we do is we superimpose them together. So writing our forces f of t in this piecewise manner means we can write our response also as a piecewise function. So here, this x1 of t, well, that's the closed form response due to just f1 of t. And what we do for the second interval, where we apply this second force, is we copy our response from before, and then we superimpose or we add the response from that second force. So x2 of t minus t1, that's the response of our system just due to the f2 that we have in our f of t. Then when we reach the third interval, where that third force is imposed, we copy our entire response from above, and we add on or superimpose a third piece of it, the response of our system due to that third force being introduced. And then from there, we keep going for however many intervals we have to cover. So we can aggregate or put together all of these forces and come up with our piecewise solution to what the behavior of the system looks like, this x of t. But what we have to keep in mind is we can only go from this f of t to this x of t if we write our f of t in this cascading manner, where we keep adding another force on and kind of tallying all of our forces together.